Alright, so today's video we're going to take a look at a continuation of what we were doing with section 6.1, which was looking at differential equations where we were unable to necessarily solve them, and we did a graphical approach by looking at it via the slope fields. So it was this idea that if we are trying to solve a differential equation, which means to find the general solution, the general antiderivative, that one of the techniques that we could do is, instead of solving it analytically, which is going to be to find the actual antiderivative, that sometimes it's good enough to simply take a look at the slope fields and figure out where the general antiderivatives would be headed toward, using your slope field kind of as the arrows or the guides to tell you where to go. What we're going to do now is I'm going to combine in this set of notes. You're actually doing both 6.2 and you're going to be doing 6.3 in your textbook. 6.2 is really more of a review from pre-calculus, where we look at exponential growth and decay, and then 6.3 is going to look at the technique of actually analytically or algebraically integrating the differential equations by separating. All right, this part over here where it talks about Euler's method, just as a comment, in the AP class, this is not something that you need to concern yourself with. That is not on the AP, so we can pretty much take that out as something that we are concerned about. It may be something that we come back and play around with after the AP, but for right now, we're going to skip over that and go straight to separable differential equations. All right, so our idea here is, and we've already talked about this a little bit, I mean, this is one of the easier sections on the AP, that a separable differential equation is one in which we're going to be able to take all the x's and dx's and separate them from all the y's and dy's. That we're going to be able to get on one side of the equation all the x's with the dx, and on the other side of the equation all the y's with the dy. That we're going to be able to put it essentially in the differential form, but there may be some extra y's hanging out in there. It's kind of like almost an extension of the implicit differentiation that we had done, and it's working backwards from when we do not have a formula that is explicitly solved for y. All right? And kind of one thing that's very important here, and I can't stress this enough, that it is very, very important that when you solve a differential equation, that you show the separation of variables. That step that you are going to have to put in is going to be always worth at least a point in the free response. And if you don't show that step, then you don't get that credit. So you want to make sure that you do that every single time. But it's a very simple step, and so it's fairly straightforward. So suppose over here, and they've actually already gone to show you several of these solutions, general solutions, to this differential equation. If we had had slope fields on this, then we probably would have had several little pieces coming across here, and we could go through each of these and determine the slope and have the slope fields. But we're basically saying, hey, we're going to be able to solve this differential equation. Here are several of the general solutions that are dependent upon the initial condition and the c values that we're going to find for those. So the first thing, here's what we're trying to solve, just to kind of bring down and show you our work. Our dy dx is going to be equal to x squared over y squared. And you can see that it's not as simple as simply moving the dx over to get it in differential form. What you see is that you have an implicit formula where your x's and your y's are mixed together. And so the idea here is that as long as we can separate the x's from the y's, we are going to be able to integrate this. And kind of the rule of thumb for you guys is, as long as it's multiplication or division, it's going to be easy to separate. When it is addition or subtraction, it's going to be difficult. You would have to factor to turn it into multiplication or division, or do some manipulation in some way to help you separate. But what we mean by separate is, I'm simply going to multiply both sides by y squared and move the y squared over with the dy, and then I'm going to multiply both sides by dx, and move the dx over with the x squared, so that you can see that on one side, everything on the left side is in terms of y, everything on the right side is in terms of x. This is the step that you need to show. This is our separation of variables. All right, and then once we have shown our step for our separation of variables, we are going to integrate it, and it's perfectly fine to come in and give your integration symbol right on that step because they can see that we've separated. Now we're just going to take an antiderivative. Same rules as we've had all along. The antiderivative of y squared would be y cubed times a third. Now, I'm going to wave my hands for a second. I'm going to put this in very lightly and say, hey, there would be a plus c there. Or actually, let's do it a little darker so we can see it. That plus c, when I am working this problem, notice, maybe we call that c1, that over here on this side, when I do the antiderivative over here, I'm also going to have a plus c. But what we see is that we're not really going to keep this as two separate c values. What we're going to do is we're going to combine them together, because your first step would simply be to move this over, and when I subtract c1 from both sides, c2 minus c1 is a constant. So we're going to turn this into a mega constant. Most of the time you come straight down here and you just say 1/3 y cubed. You know there's a constant, but we're just going to do one big mega constant on this side. And then we just go 1/3 x cubed plus this mega constant. So it's kind of like where, yeah, I know that there would have been one on either side, but we're going to combine them together anyway, so we always just kind of stick them together and say plus c. It's the same thing of when you're integrating over a sum. Each time I integrate, I don't put plus c. I just wait to the end and put the plus c on. So this right here would be our general solution to the differential equation. And that's always your first step. You, 1, separate, 2, get your general solution. And then we move on to the particular solutions, and we're finding 3 different particular solutions. Really, I guess I should have went, this is A, this is B, and this is C. That we're going to find 3 different specific particular solutions using this given information. So for A, and again, all you're going to do to find your particular solution is you're going to plug in. So when y of 0 equals 2, and basically plugging in, you could solve this for y. I mean, there's 2 options. You can, once you get your general solution, you can either leave it in implicit form, or you can solve for y immediately. And it's one of those things that it's really going to be up to you what you decide to do. A lot of times what happens when we're looking at this, and this is partly why, if you'll notice over here on my solutions, they don't appear to be vertical shifts of each other. And the reason for that is because this constant, this was not equal to y, it was equal to 1/3 y cubed. That if I actually continue this on and solve for my y cubed would equal, multiply by 3, would give me x cubed plus, now, yes, it would be 3c, okay? But when you do 3c, that's a constant. So again, we just kind of absorb it and go, it's plus a constant. This is, you kind of wave your hands a little bit when you're doing this. And every time you end up with a bigger constant than what you had, that's fine. You just keep calling it c. We know that this c and that c are different. If it bothers you, you can call this c3, that c, but don't get into it. They don't care. They just need you to recognize that you have a constant when you're looking at it, and so they don't really care if you call it c1, c2, or c3. Just absorb it in and call it c. And then we're going to take the cube root of both sides to get your explicit form for y. So y equals the cube root of x cubed plus c. Now this is where you don't get to wave your hands. You're not allowed to distribute a power over addition. So don't go, hey, this is the cube root of x cubed plus a big mega constant. You can't separate this one. Now when you look at that, then what you'll notice is depending on what C is, you'll get a different one of these curves. Now you might be wondering about how I'm going to get this straight line in here. Well, let's take a look at it and find the three particular ones. So when y of 0 equals 2, I can use this form right here. Basically plug in my 0. I'm going to get the cube root of C ends up being equal to 2, so C is actually equal to 8. So my particular solution from here is going to be particular solution when y of 0 equals 2 is going to be y equals cube root of x cubed plus 8. Okay. Now let's look at B just to kind of show you the difference. For that one we had y of 0 equals negative 2. So we're doing when y of 0 equals negative 2, so that should be fairly easy. Negative 2 equals the cube root of C, so C is negative 8 in that case. Alright, so my particular solution for B when y of 0 equals negative 2 is going to be y equals cube root of x cubed minus 8. And so what we can see up here from these two solutions, at 0, 2, 0, 2 I believe would be this one right here. So when you get 0, 2, the particular solution that I'm looking at is going to be this one. So I would be on this solution when y of 0 equals 2. That would be where the constant would put me. If I'm going to be looking at the second one, when y of 0 is negative 2, that would be this solution in my family of curves. So that would get me to here. Okay. And so, yeah, there's a little bit of a difference in between these. And the difference is they're not just vertical shifts of each other, because the constant is inside of the cube root. And then if we take a look at part C, that last one, and in C we had y of 0 was equal to 0. Well, if that's true, then our cube root of C ends up being equal to 0, so C is 0. When I put that back in for my particular solution, when your y of 0 equals 0, I end up with y equals the cube root of x cubed plus 0, which is really just the cube root of x cubed, which, hey, that's x. So my particular solution is really just y equals x to go through that line. And that's where this line is coming in here. So what we're going to see is when we have an implicit form, that when you have a derivative that's in its implicit form, that your constant that you end up with and then end up solving for y typically is inside of some function. And that when it's inside, that causes different types of behaviors in the family of functions. And we were starting to see that when we did the slope fields as well, that it doesn't turn into this nice family of functions that all look alike, that they have different characteristics depending on what point that you pick, and that will help you figure out where they go. All right? So that's the idea with our differential equations, that the first thing you always do is step 1, you separate. Step 2, you integrate. Usually after you integrate, you solve for y, if you can. And then the third thing that you're going to do after you solve for y is you use your initial condition to find your particular solution. And so hopefully you can start to see why when you have the quote-unquote families that you're getting by looking at your slope fields like you have here, that you may bother you that these don't all appear to be parallel to each other like they would if it was a plus c on the outside. We would not expect them to have a family of functions that are vertical shifts of each other, because when I look at my rate, my derivative, it is in an implicit form. So hopefully that will kind of help you also a little bit when you're looking at your slope fields, that I have slopes that depend on both the x and the y. And again, this is two separate initial conditions, so this is going to be an A and a B. All right, so I'm going to start with my derivative, and I'm going to use my steps. We have dy dx equal to x squared y. We separate. I'm going to divide by y, 1 over y dy. And then over on this side, bring my dx over, x squared dx. So step 1, you separate. Step 2, then you integrate. So we can go ahead and put our integral symbol in. We have to show that to show what we're doing. So we have natural log absolute value of y. We're going to put the plus c over at the end over here. If that helps you, just go ahead and write it first. And then I have again 1/3 x cubed. So that gets me to a implicit form of the general solution. So now I'm going to solve for y. So 1, we separated. 2, we integrated. And now we're going to solve for y. Which basically, using your log properties and your exponents, I'm basically going to raise both sides to the e, or not really raise, I'm going to put e to each side, apply the exponential. They would cancel over here. Absolute value of y is going to be e to the 1/3 x cubed plus c. Now we could leave that there, but then we can also recognize that e to a power is always positive, so the absolute value is now no longer necessary. And we're also going to do a little trick over here, and they pretty much always do this. Applying exponent rules, this is the same when you multiply like bases, you add your exponents. So they kind of break this off. And because e is a constant and c is a constant, we are going to do that absorbing again and turn it into the mega constant and kind of say, hey, we're going to have our constant, this mega constant c, which is really e to the c, and e to the 1/3 x cubed. And again, because our ultimate goal is to find a number to have in that position so that it works out. It doesn't matter that this c is not the same as that c. We're going to find a number to put in this location. Okay, and we're recognizing that it's just a number. So I separated, I integrated, I solved for y. Okay, now we're on to the next step, which is given some particular initial conditions. So when f of 0 equals -2, and then you'll get to see why we like this. -2 equals c e to the 0. Now remember your property, e to the 0 is 1, so this pretty much always drops out, and we're left with c equals -2. So our particular solution, when f of 0 equals -2, is going to be my y equal to -2e to the 1/3 x cubed. And let's take a moment and look at that on our calculator. Alright, so after you put it in your calculator, here's what that solution looks like. And as you can see, you see the kind of shape that we have right here? If I had gone through -2 over here, and then follow the curve of the slope fields, so you're going to kind of come along here, and then you're going to start curving up, and then as you start curving up, eventually you're going to start coming back in this way, and then we're going to continue this way, kind of following along, kind of along this line. And then so if you take a look at that, you can see how the slope field and this curve that we can sort of eyeball and squint and get from the slope field where that comes from when you go through that point of interest that you're looking at. All right, now the second one, just to be thorough here and do both parts. B, when your f of 0 equals 1, and again, partly the reason why we like this is because that's going to go, we're going to get c equal to 1. So your particular solution is going to be y equals e to the 1/3 x cubed, and that's going through 0, 1. And so if I were to take a look at that, then again, we could graph it on our calculator. We could sort of follow along with our curve here and then coming back over on this side, following our slopes. We would probably have something that looks like this. And we can just double check that real quick just to be thorough. If I come back in here, all I have to do on my y equals, all right, is do our e to the 1/3 x cubed. Okay, since we found out that our y was 1, and then we take a look at the graph. And again, I'll move over so we can do a comparison. You can see our kind of shape that we had that we were sketching in from our slope field. All right, so that's the idea, that we first separate, integrate, solve for y, and then use our initial conditions over here for part 3 to find particular solutions. And then if we have our slope fields, we pretty much already know what they're going to look like. All right, here's another example. This was from an actual AP test, and you'll start to see that these are fairly standard when you're looking at it. You've got a function f. They're giving you a point on the function. The slope is given here, and we see that this is an implicit form of the slope. So let's just kind of go through this and see what they're asking us to do. First, we want to find the slope of the graph at the point where x equals 1. Now, because this is an implicit form, we know that we actually need the x and the y, but we will remember from up here that if f of 1 equals 4, they're basically telling me the point 1, 4. So the slope, dy dx, remember your notation, when evaluated when we have 1, 4, and we simply just have to show the work for that. 3 times 1 squared plus 1 over our 2 times 4, which is going to give us 4 over 8, or 1/2. So that's fairly straightforward. All you had to do was recognize they gave you the point that you needed, and your slope was implicit, so you need to plug in both your x and your y. All right, now for part B, we want to write the equation of the line tangent to the graph at x equal to 1 and use it to approximate f of 1.2. All right, so you see there, we're going back to when we were doing linearization. So for part B, all we're trying to do is to find the linearization. Our tangent line at x equal to 1, we're using our point from above, 1, 4, our slope that we found in A, which is 1/2. So my tangent line equation is y equals 1/2 x minus 1 plus 4. Done with that part. Then it asks me to approximate f of 2. So f of 1.2 can be found by approximating, and we're showing we're using our tangent line approximation, 1.2 minus 1 plus 4, and you can either leave it there, you can do a little arithmetic. This is not hard. This is 0.2 times 1/2, 0.1, so we're going to end up with 4.1. All right, so we've approximated f of 1.2 by using the linearization, and we got 4.1. Now, sometimes at this point they may come in and ask us to evaluate whether this is an over or an underestimate. They did not ask you in this case, but I just thought I would mention it, that if I wanted to discuss the over/underestimate, what you would do is you would need to figure out the second derivative to determine concavity. So you would find the second derivative with respect to x squared, and then you would evaluate your second derivative at the point 1, 4 to determine whether it is greater than 0 or less than 0, and then use your concavity as your choice to help you choose over or underestimate. They didn't ask us to do this time, but I thought I would review while I'm here. All right, so now let's move on to C. Let's see what they're asking. They want to find f of x by solving the separable differential equation. So right there is also code that you better show your separation. So in your work, you would have your 2y dy equals your 3x squared plus 1 dx. So you show the separation. Then you show you're going to integrate. So we find our general antiderivative. So we have y squared. Yes, we're going to have a plus c. And then this would be x cubed plus x plus c. So you get to here. Now you can either at this point find c or solve for y. It doesn't really matter what you do when you want to find your particular solution right here. Usually they do want you to solve this for y because they did say find f of x, which implies that you need to solve for y. Okay? And we want to do it with the initial condition f of 1 equal to 4. So I'm going to go ahead and solve this for y. So y would equal, now technically plus or minus the square root, x cubed plus x plus c. Now we're going to, this is our general solution. Now we want to find the particular solution when f of 1 equals 4. Now here's where you have to be careful though too. When f of 1 is 4, f of 1 is giving you a positive y value. This has a plus or a minus. So you have to choose which one. So choose the plus or minus based on your point. So you're going to have options here. So now it should be obvious. The y value is positive 4, so I have to be choosing the positive one. So I would do the y equals positive square root x cubed plus x plus c. I'm going to plug in my 1, 4. So 4 equals the square root of 2 plus c. 2 plus c equals 16, so that's giving me that c is equal to 14. So my particular solution is going to be y equals square root x cubed plus x plus 14. Now you could have done this where you found c up here before you solve for y, because that's all just to kind of show you the difference. You're basically plugging in 1, 4, so there's nothing to say you couldn't plug in before you solve for y and get 16 equals 1 plus 1 plus c and get c is 14. So, and that actually worked out pretty faster than what we did down here, but yet once you get this, you still have to choose the correct particular solution to go from here down to the y equals, or f of x equals ry, which equals this. Okay, so that was part C, and then we have one more step. Use our solution to find an actual value for f of 1.2. And so on this, all we're going to do is take our f of x and do f of 1.2 and plug it in. Square root 1.2 squared plus 1.2 plus 14. And if you have a calculator, go ahead and take it to your 3 decimals. If you don't have a calculator on the free response, just leave it there and they're fine with it. All right? Now, let's take a look at, this is now, that was pretty much section 6.3. Now what we're going to do is we're going to go to a special case of separable differential equations where we're talking about the law of exponential change. Now remember we've been talking about this e to the x, that was actually the really important function because e to the x's derivative was itself. So at any point on e to the x, its rate of change was its y value. And when we're doing exponential growth, they don't all have a base of e to the x. When I do the derivative of b to the x with respect to x, the derivative of this, if you will recall, was a constant, ln of b, constant, times your b to the x. So it was always proportional to the rate of change. And so this is kind of this kind of rule about exponential growth and decay, that the more you have, the more you get. And so when we're looking at these exponential growth and the decay, the less you have, the less you lose, the quantities are always going to be this idea that your rate of change is always going to be directly proportional to the quantity itself. And we see that above because here's your K, your constant, and this was your quote-unquote Y value that you had. Your rate of change is always proportional to the actual how much it has, the quantity itself, the Y. And so that's a characteristic of exponential growth and decay. And this constant, this ln of b that we have there, is going to tell us whether we have a growth or a decay, all right? Because that should kind of make sense to us when we're looking at it. So the idea, we're going to show you why this is a separable differential equation, and then we're going to tell you what you need to memorize, because we're going to do, this is almost pre-calculus, because the way that we get our solution is calculus, but actually doing the problems is a pre-calculus topic. If I'm going to separate, it doesn't bother me that I have y's and t's. My variables are y and t. One side needs the y's, one side needs the t's when I separate. K is a constant, so it can go on either side, and I'm just going to leave it where I have it. So I'm going to end up with 1 over y dy equals k, a constant, times dt. Now this is where you're going to see, and we've already seen this in several examples, that this is where you're getting the exponential part, because the antiderivative, so I've separated, now I'm going to integrate. The antiderivative of 1 over y dy is always natural log absolute value of y equals kt plus the constant, right? We're going to bring that in. But then we always need to solve this for y. And so solving it for y pretty much always means get rid of the log, put it back into exponential form. So e to the kt plus c is going to be equal to our absolute value of y. And then we use common sense and drop the absolute value, because exponentials are always positive. And we absorb, just like we did before, I'll show it one more time. We go e to the kt times e to the c, that this constant, you add your exponents, and then we call that the quote-unquote mega constant, and so it becomes y equals c e to the kt, where this constant is really e to the c, but we're waving our hands because it's just a number that's there. And we do that because this form is the nicest form to work with in the problems. Now, the nice thing about this is, do you have to show this every single time? No, you don't. You can go straight from here and going, oh yeah, anytime the rate's proportional to the value of y, it's always going to be exponential. So that would get us to here, right? So basically, memorize this. And then this is nothing more than pre-calc problems, because your job is simply going to be use this form, and then you have to find c and k. You have two constants. You will need two pieces of information. So let's take a look at this. Like I say, and this is so easy. It was something you did last year in pre-calculus. We have bacteria. It increased from 400 to 1600 in 3 hours. So we can assume that at time 0 we have 400, and at time 3 hours we have 1600. So they're giving you 2 points on the curve. Why did they give you 2 points? Because you have two constants you're going to find. Then they tell you we're going to assume that the rate of increase is directly proportional to the population. So as soon as we see that, we know, hey, exponential growth or decay, I know that my model that I am going to use is y equals c e to the kt. Do you need to separate and show, do I need to start here and go, hey, dy dt equals ky? Do I need to show that? Not really. They're just going to assume that if this is what they tell you, then you automatically use that model for your formula. Now we're going to have to actually find c and k using our given information. And the nice thing about this is whatever you have as your initial amount, that 0, 400 will always find c for us, because we have 400 equals c e to the 0 times k, which is always just going to be c equals 400. You actually don't even need to show this work. You can immediately go, hey, 0 equals 0, 400 means c is 400, and we're done with that part of it. Then the second part is we've got to find k. So our model at this point is 400 e to the kt. Now I'm going to use the point when you have 3 1600. So 1600 equals 400 e to the 3k. And then you just have to use properties of logs. This is like pre-calculus. Divide by 400. E to the 3k, take the log of both sides. Natural log of 400 equals 3k. Divide by 3. K equals 1/3 natural log of 400. Done. Of course, haven't answered the question. An appropriate equation to model this. So the equation to model the population is going to be y equal to, and we have our c, which is 400, e to the k, 1/3 natural log of 400 times t. And then we can pretty much say we're done with that part with A. Now B, and I'll talk about this tip here in a second, B usually is find the number of bacteria at the end of 6 hours. They're basically just asking you to find y of 6. So we would take our 400 e to the 1/3 natural log of 400 and times our 6, and we would plug and chug and we would get our answer for that. And then we're done with this problem and we're going to walk away. I'll let you get the 3 decimals. Now, one comment that we want to make is that sometimes in this problem that e to the k is really, think of that as your base b in this problem, kind of relating it to where I started above. And so sometimes what they do here is instead of solving all the way for k, like I did there, what they do instead is they solve for b, the base, which is e to the k. So if I come back up here to where I have, this would be my e to the k to the 3, right, just coming right back here to this step, is equal to 400. So e to the k is going to be the cube root of 400, or 400 to the 1/3. And so a lot of times when they do this model, they'll write it as y equals the 400, which was your constant, times your base, 400 to the 1/3 to the t, which is going to give you 400 times 400 to the t over 3. That they like it in that form without the e. Now, and then just to prove to you, using your pre-calc from last year, that they are the same models, if I have 400 e to the 1/3 natural log of 400 to the t, that's the same as, remember your log property that says if you multiply by a number you can write that as a power. So that's the same as 400 e to the natural log of 400 to the 1/3. Of course, that's all to the t. And oh, wait a minute, e to a natural log, that's just going to cancel out. So this ends up being 400 times, now remember that also kind of properties of exponents, that when you multiply, that it's this raised to another power of t. So it really ends up being 400 to the 1/3 to the t, which is exactly 400 times 400 to the t over 3. That those are just different models, and I'm really just playing around with pre-calculus concepts, log properties and exponent rules. They don't care in calculus whether you leave it up here in this form or whether you put it in that form. They are all the same. That's really what our point is on this example. All right, let's look at example 6. This is a calculator. We're losing its mass at a rate that is directly proportional to its mass. So its mass rate that we're losing the mass, dm dt, is directly proportional to its mass. Okay, there you go. Guess what? That's going to be our exponential growth and decay. As soon as you see that in A, I want to find a formula. You pretty much can take that change in mass with respect to time being proportional to its mass, is going to turn into, after you separate and solve, to our mass equals our exponential growth, a constant e to the kt. There you go, done. Don't even have to show the calculus portion of it. It's like, here you go. I can separate and solve that. And usually you see these in multiple choice questions a lot. So that would get us to here. Now I need to use the information. I got to have some given information. They gave me that the half-life is 1590 and we started with a mass of 100. So I know that 0, 100 would be 1 point. And I know that it's half-life. So 1590 years later, I would have half of what I had, which is 50. So I basically look in my problem, I find the 2 points they gave me. Now I'm going to find the constants. I already have C. C is going to be 100. So M equals 100 e to the kt. Then we're going to plug in our 50 and our 1590. So then we would go 50 equals 100 e to the k times 1590. And you should notice that this is always the same. Hey, look, 1/2 equals e to the 1590k. If we want to go all the way down to k, we would have natural log of 1/2 divided by 1590. If you want to just solve for e to the k would be 1/2 to the 1 over 1590, right? Because isn't that the same thing? If we were to pull the power, the inside, I'm multiplying by 1 over 1590, so I could bring it in as a power. Either way you go, your model is going to be your mass is equal to your 100. I'm going to leave it in the e form because I like it that way. E to the, where's my k? Natural log of 1/2 over 1590 t, or, just for being thoroughness, I could write it as 100 times 1/2 to the t divided by 1590. Either of those would be acceptable answers for A. All right? Now, obviously, I write way too big for this, but let's look at B. Find the mass after 1,000 years. So all they're doing is say find the mass after 1,000 years. Plug it in. 100. I'm going to use the second one. 1/2 to the 1,000 over 1590. And I will leave it for you to go get your 3 decimals because this is a calculator problem. All right. And then C. Let's do C over here. When will the mass be reduced to 30? So we put 30 in for the mass, set it equal to, and again, I don't care which one you use. I'm going to continue with the 1/2 one. T over 1590. Divide by 100, so that's going to give me 30 over 100, which is 3/10 or 0.3, equals 1/2 to the t over 1590. I'm going to take the log of both sides. Natural log of 0.3 equals, bring your power in front, t over 1590, natural log of 1/2. All we're doing is exponent and log rules. Divide by natural log of 1/2, natural log of 0.3 divided by natural log of 1/2 times 1590 equals t, and then we will leave you to plug it in and get your answer of how long it takes. Fairly straightforward problem when we're taking a look at it. All right, let's look at example 7. The amount of oil pumped from the canyon wells decreases at a continuous rate of 10% per year. When will the well's output fall to 1/5 its present level? All right, so that if they're telling us that the rate is continuous rate of 10% per year, so they're telling us that the amount you lose is 10%, and you lose, so it's negative, of how much you have. Oh, wait a minute. Our rate is proportional to our amount that we have. Wait a minute. They already found the K for us. This pretty much goes straight to our formula for our oil is going to be a constant, okay, times e to the negative 0.10 t, that our amount that we have is always going to be found. We know that our rate is proportional to the amount we have. Oh, it's exponential. There you go. The only difference in this problem is I gave you k. I told you that k was, I lost 10% each year, so k is negative 0.10 t. And so basically right there, now I want to know when the well's output will fall to 1/5 of its present level. Well, it doesn't really matter how much I start with. I don't actually have to find C. I want to know when the output is 1/5 of the present level. And the present level, if you remember, C is your initial amount, that's your C. So you're pretty much saying, when will I have 1/5 of C as my oil? And I can just plug that in. The C's are going to divide out, so really all you're trying to solve is when is e to the negative 0.10 t equal to 1/5. Take the log of both sides. Negative 0.10 t equals the natural log of 1/5. And then divide by negative 0.10, natural log of 1/5, divided by negative 0.10, and then I will leave it to you to get your answer. Do make sure, just as a reminder, because I'm skipping through some things here, answer the question. The well's output falls to 1/5 of the present level after, and then put your decimal that you find right there. So do make sure you answer the question. Probably same thing coming back up here for C. The mass will be reduced to 30 grams after, and then this value that's there. So make sure you're answering the question. All right, let's take a look at 8 and see how that one works. So we have a population of fruit flies. They're growing in proportion to the number of fruit flies. Grows, rate of change, in proportion to the number of fruit flies. So we pretty much know that our population P of t is going to be C e to the kt. See, look, I didn't even need to use calculus there. Once I know the rate is proportional to the number you have, hey, it's exponential growth. That's all the calculus is using. And then we say if there were 100 flies after the second day and 300 flies after the fourth day, how many flies were in the original population? So after the second day, okay, so at the end of day 2, you had 100. And then after the fourth day, you had 300. Now we want to figure out how many were in our original population. So now let's go back to pre-calculus. We've seen problems like this before. What we know from the 2 100 is going to be that we have 100 equals C e to the 2t. Oops, 2k, sorry. Figure out where I'm plugging things in for. Plug in 2 for t, so I get 2k. From the second point, I know that 300 equals C e to the 4k. And oh, we have a sort of like a system. But in our world, for a system, the easiest way to do this is always to go 300 divided by 100, do a ratio, set up a proportion, is going to be C e to the 4k over C e to the 2k. And oh look, the c is going to go away. This, we're going to use our subtraction property. This is going to be e to the 4k minus 2k is going to equal 3. And natural log of 3 equals 2k. K equals 1/2. Natural log of 3. So we kind of set up a proportion and solve for k. That's going to get us back to our original here. We're going to have P of t equals C e to the 1/2 natural log of 3t. And now I'm just going to pick either point. Doesn't really matter. I'm going to use the 2 100 to now find C. So I'm going to plug in 100 over here. And then I'm going to plug in the 2. And we're going to end up with C e 1/2 natural log of 3 times 2. Oh look, this and this will cancel. e to the natural log of 3 is 3, so 3c is 100, so c equals 3 over 100. And so how many flies were there in the original population? Okay, and I'm staring at this because I'm dyslexic. I took 100. I was trying to figure out how I could have only 3/100ths of a fly. It's 100 divided by 3, so C is 33 and a third. Now, how many flies? You basically need to either round up or round down, probably in that. This is more of a fake problem than it is one that you'd probably see on the it'll probably say to the nearest fly how many flies were in the original population, of which you'd say there were 33 flies in that one. All right, so let's take a look at our last problem. And oh, look, 2008. We've been working on the multiple choice for 2008. Here's an example of what was actually one of the free response questions in 2008. So we have a differential equation given to you here. Notice it's an implicit form. So we know that it's not going to be the family of functions where they're all parallel to each other. But what we do know is that we want to do a slope field. And then we want to find a particular solution. Okay, because we're going to have to separate and integrate and then plug in and find the constant. And then we're going to find, for this particular solution that we found in part B, we're going to do a limit and see what happens. All right, so the first thing is, let's go through at the 9 points indicated. So even though there's a 2, a 1, and that's not points, I'm looking only at the points that are indicated. So basically we just plug and chug. I put in, this point is -1, 0. If you have to show work, please do, but you don't necessarily need to. You're just like -1, 0. dy dx is going to be 0 minus 1, -1, over -1 squared. So I get -1. And we kind of sketch in our little slope of -1 for that one. If I plug in my -1, 1, then my dy dx is going to be 1 minus 1, 0, over 1, which is 0. So then we have this coming across. To be honest, the biggest thing here is just not to make an arithmetic mistake when you plug them in. That's really all it is. Don't put the x in the wrong spot. Don't put the y in the wrong spot. Just pay attention to where you're plugging and chugging. Then I have -1, 2. So dy dx is going to be 2 minus 1 over 1, or 1. So I fill that in. Try to make sure that these are opposite each other. Remember, they're looking at your 1s, your -1s, your 0s, and your verticals. That's really what we're looking at. Then I try 1, 0. And when I put in 1, 0, well, that's still going to be -1. So I start to see a pattern. If I put in 1, 1, 1, 1 is still going to be 0. If I put in 1, 2, 1, 2 is still going to be +1. Why? Because the only thing I changed was the x, and 1 and -1 when you square them are the same. Now we get to 2. This one gets more interesting. If I put in 2, 0, I'm going to get -1 over 4, so -1/4. So here's -1. -1/4 is less steep, so make sure it comes across as less steep when you're sketching it. Then 2, 1 would get me 0 over 4. Oh, so we're back to horizontal here. And then 2, 2 would get me 1 over 4, so 1/4. So again, a little bit less steep, and try to make it the opposite of what you have there. So they're, in comparison, going to be like, if that's their 1, this better be less steep when you come across. So that's all you have to do for A. Easy. Just don't make an arithmetic mistake. So A, done. Now I'm going to go for B. Find a particular solution, and I'm using f of 2 when f of 2 equals 0. So step 1, separate. So we have our, now be careful here because the x squared's in the bottom. What you really want to do is multiply by x squared, and so I have 1 over x squared dx. Okay? And then we want to have the y minus 1, so it's going to be 1 over y minus 1 dy. So there's our separation. We show the step where we separate. Then we integrate. Now this is log. It is a u substitution, but basically the derivative of y minus 1, if I do u equals y minus 1, du equals dy. So I can pretty much just go, hey, this is natural log absolute value, y minus 1 over here. And again, you're going to do plus c at the end. This is going to be, power rule, x to the negative 2. I add 1, x to the negative 1, and divide. So don't get yourself lost on that. Don't go, oh yeah, it's log. It's not log, that's power rule. So we get to here. I'm going to solve it for y because they want it to be find the y equals f of x, which means solve for y. So I'm going to go ahead and do that here. So this becomes e to the negative 1 over x. And I automatically, when you have this plus c, I'm just going to go times c. Just switch it automatically. You don't need to see the step in between. And I always drop the absolute value because it's not necessary when you have your exponential. Exponential is always positive. And then we do y equals ce to the negative 1 over x plus 1. Now I'm ready to actually plug in. So when f of 2 equals 0, we get 0 equals ce to the negative 1/2 plus 1. Remember, we're solving for c, so I'm going to subtract 1 and divide by e to the negative 1/2 or multiply by e to the 1/2. So we get negative e to the positive 1/2, and that would give me my c. Okay, so my particular solution when f of 2 equals 0 would be y equals my negative e to the 1/2 times e to the negative 1 over x plus 1. If you wanted to, because these have the same bases, if you wanted to write it as negative e to the 1/2 x minus 1 over x plus 1, feel free. We don't care. It's either one or the other, and they're perfectly happy with both. And so that is the particular solution, solve for y with the initial condition there. If you want to, maybe we should go ahead and put f of x equals, just so we got y equals f of x in there. Now we want to find, for this particular solution, I want to take the limit as x goes to infinity. So part C, now I want to take the limit as x goes to infinity of f of x, show that I know that they're doing the limit as x goes to infinity of negative e to the, I'm going to use this version, e to the negative 1 over x plus 1, and they're basically just testing you on how do you know what happens. The limit of e, as this goes to infinity, what happens to this? This goes to 0. E to the 0 is headed toward 1. So we end up with basically negative e to the 1/2 plus 1. And then we're done. So I sort of did that, kind of substitution thing in there. The limit of a constant is a constant, and then the limit, you figure out what happens here. Composition, I am cheating, in my head I'm doing the limit as x goes to infinity of negative 1 over x equals 0, right? And then remember that becomes the new limit. The limit of a constant times anything is the constant times the limit, so negative e to the 1/2 times the limit as x goes to infinity, as x goes to 0 of e to the x, and that's now nice, so that goes to 1, and so I get negative e to the 1/2 times 1, and then of course plus this 1 that was over here. So I was doing limits with composition sort of in my head, and they don't need to see all of this work over here. All they really need to see is, once you get to here, that you are taking the limit and you get 1 minus e to the 1/2 on that. And that was actually the free response. That's not too bad for a free response. I mean, most people got this part right. As long as you separate it over here, you are okay. Don't get lost in the middle of finding your constant and then finding a limit, which was prior knowledge from chapter 2. All right, and that's it, and that will finish up these notes.